we're going to talk about the equation today that gives us exponential growth and decay. And we kind of already talked about this a little bit with the graphing part of it. And today we're not going to so much worry about the graphing as much as solving for different variables and using the equation to answer certain questions that we have. Most of these are going to be story problems that represent exponential growth and decay. And so we'll look at some examples of some things together here. I'm going to do 2 examples with you, and each problem has multiple parts to it where you're going to be doing different things throughout the problem. Before we do any examples, though, let's talk about the equation itself. This looks very similar to the PERT formula that we did with money because it's basically the same idea, but it doesn't always deal with money. And so that is the formula. And you could do it with money, but other examples where, like, you might talk about like the population of a city or a county or a country, or maybe the population is growing exponentially over time, or maybe it's decaying and losing population. Maybe it's like a species of animal. Like if it's becoming endangered, then obviously the population is decaying over time. You could talk about like the virus, right? Like we saw that a while back, where the number of cases grew exponentially. So those are all examples. So obviously we can do it with money, but we can do it with a lot of other examples as well, where we see some number of cases or the number of things growing or decaying exponentially. P sub 0 is the starting amount. At time 0. So that's why we call it P sub 0. Okay, so that is like, if we said we're going to start collecting data in 2000, and then 25 years later, where's the population or whatever at, then that's 25 years. Because we started in 2000 and then 25 years later. So 2000 would be time 0, our starting point. K is going to be the rate. In the PERT formula, we used R, and you could use R if you want to, but I think they use K here. If it's a positive number, that represents growth. If it's a negative number, then that's going to represent decay. So you could have a positive or a negative K value, and that'll tell you what direction it's going. And then T is time, and time is the number of years since T equals 0. Okay. So you gotta know the starting point, and then how long has it been since then. 10 years, 20 years, however many years down the road. All right, first example that we're going to do, we're going to use this formula over and over again today. This is on page 391. I'm going to start with number 14. Yep, 391. Okay, so number 14 is talking about a classic car. And it says, in March of 2023, a 1962 Ferrari sold for $18,045,000. The car was purchased in 1972 after it had been damaged for $2,400. Assume the value V of the car is growing exponentially. Okay, so 1972 is the starting year. That's the one thing we want to identify first of all, because that's when we bought the car initially. Okay. When I do my formula here, P sub 0 is going to be the amount that we start with. And it tells me right there, and they use V sub 0, so it really doesn't matter. V just for value of the car. P sub 0, V sub 0 all means the same thing. So they tell me right there in part A, that's my starting amount. T is the number of years after 1972. So in 2003, 23, sorry, minus 1972, how many years have passed? 51. Okay, so 51 would be my T value. Okay. We want to find the value of K. Well, in 2023, the value of that car was $18,045,000. We know everything except for K. K is what we're trying to find. So we got to solve for K. That's what the part A is asking us. What is the value of K? So the first step is we got to get rid of that 2,400 out in front. So we're going to divide by it. Okay. And you're going to need your calculators out for this, obviously. You're going to deal with some big numbers here. Okay, so we get 7518.75, if I typed it in right. Okay. Our goal is to solve for K. Now we've seen problems like this the last couple of days. If I wanted to get K by itself, what are we going to do? Since K is in the exponent. Do what? Yep, and before we frog it, we have to log it. And so what I kind of like to do here, log it, frog it, solve it is going to be our process, but you can kind of combine two steps into one here. Because we have an E on the right-hand side, we're going to use ln. So we're going to do the ln of both sides. And I'm going to combine two steps into one here. I'm going to log it and frog it at the same time, just to save some time. ln of E is really 1. Okay, so we're going to take the ln of 751875, the number that we just got, and we're going to divide by 51. Okay, and I'm going to round to the nearest thousandth, 0.175. What that means is that this car value is growing at 17.5%, which is pretty crazy over time. But to go from 2,400 to 18 million, it's a pretty good jump, right? Even though it went over 51 years, it's still a pretty incredible jump in value. Okay, so that's part A. What is the value of K? Part B wants to know, estimate the value of the car in 2030. So we're going to use this formula now the 2400 stays the same. We now know this is our equation. Okay, because we now know what K is. And so all we got to figure out is what T is in this case. So in 2030, how many years would have passed? Okay. So we're talking 58 years. So we're just going to plug this in. And you should be able to put this all in at once. 2400 times E raised to the, and then I would put that whole thing in the exponent in parentheses. We're just going to, I think, round our answer. So another 7 years down the road, it jumps from 18 million to 61 million. Yeah, well, whoever bought it for 2,400 back in 1972 is made a pretty good investment, I would say, huh? If that's really the case. Yeah, I just kind of rounded it.
Still like in 1972, $2,400 was a lot.
Probably was. You're right. Yeah. Okay, so then part C, what is the doubling time for the value of the car? Okay, so I'm going to show you how this works, and then I'm going to show you the easy way to do this from here on out. Okay, the doubling time means how long did it take that car to double? Well, initially it was $2,400, right? So double of 2,400 would be 4,800. Okay, and after we do it this way, I'm going to tell you you won't have to do it this way again for the doubling time, because it's going to be the same every time. Because as I divide by 2,400 here, I get 2. And then I'm going to log it, frog it, solve it. So I'm going to do the log of both sides. The ln v is 1, okay? So all we're going to do then is divide by 0.175. Oops, and then we're finding T, not K. Okay, so I'm going to round that up to about 4 years, depending on what it says to round to, and it really doesn't say what to round to, does it? So it's like 3.96, so I'm just going to round it up to about 4 years. Okay, so whenever we have a doubling time problem from here on out, we're going to take the ln of 2, we're going to divide by k, and that will give me t. Or I could do it this way. If I want to know what the k value is, I could divide by the number of years, and that could give me k. So that is the quick shortcut that we can use whenever we do doubling time. Okay, so I'm going to put a star by this because these two will be quick and easy ways to do that. Okay, if it said tripling time, we would just put 3 in here. If it said half time or half-life, because half-life is another one we might look at, like in science, how much does it, how long does it take something to decay to half its life? So then I would put in a half instead of 2. And so all you have to change is the number. If I know the k, I can divide by k to get t. If I know t, I can divide by t to get k. Okay, so that's kind of your shortcut to do a doubling time problem. And then the last part, how long will it take the car value to reach $50 million? Okay. There's a couple different ways you could do this, but we would have to put 50 million in. And we started at 2,400. And all of these are going to basically be the same problem. We're just going to be continuing to log it, frog it, solve it. So I'm going to take 50 million divided by 2,400. Okay. And then as you kind of start to figure out the process, we're going to take the ln of this number, and you could put this all into your calculator all at once if you wanted to. The ln of that number, and we're going to divide it by 0.175. Okay, that way you can kind of put it all into your calculator at once. Okay, so this is not necessarily doubling, this is just some random value. And so that's why we put the 50 million in there. And if I put that all into my calculator, we're going to get about 56.8 years. So a lot of those are just calculated problems, just plugging it in, still logging it, frogging it, solving it, and doing a lot of the things that we did the last couple of days. Okay. All right. The other one that we're going to do together, any questions on any of that so far? Same page, we're on same page, number 12 is the one we're going to do. Right, and the reason I want to do this one is because this one talks about decay. And a lot of the scenarios are going to be very similar, except growth means it's going up and decay means it's going down. Here, the numbers that we're given are quite a bit different as well. So we're talking about food decay. As food decays, its quality decreases exponentially. In a study of the decay of sugars in apples, biologists measured a density of 0.264 on day 0. So day 0 equals 0.264. So that's like our starting amount. That's where we're beginning at. So day 0 amount is the really important piece that we have. A density of 0.075 on day 15. Assume it decreases exponentially. All that's saying is that just know that we're using an exponential function. So we're going to write out for part A, the starting value is 0.264 e to the k times t. Okay, I'm just going to put in that starting value to start with. Part A, kind of like we did on the last one, says to find out what k is. Okay, what is k? Find out what that k value is. They said d of t, so probably maybe should use d instead of p in this case. I'm not going to count you off if you use p instead of d. They're just using d because they talk about density instead of p for population or whatever it is that we're dealing with. The last one, they used v, so it really doesn't matter the variable they use. Okay, 15 days down the road, the density was 0.075. We don't know k, but we know there's 15 years that have passed. Okay, 15 years later, this was the new density. The reason I start my equation off like this is because this value gets used over and over and over again. This value does not change. This value is based on 15 years. So these two numbers are the numbers that are going to change. The 0.264 will not change as I go through and do different things with the problem. Okay, so we're going to solve it. And once again, it's going to look like the same thing, right? Because we're essentially doing the same thing. We're logging, frogging, solving. I got to get rid of the 0.264 first, though. So we're going to divide by 0.264. Okay, and it gives me a decimal, and what I would say is leave that number into your calculator. So it might be better to do this. Just leave it in your calculator like that. Because then the ln of e is 1, and then we're going to take this whole thing and divide it by 15. Okay, or you could also use, if you've already divided it, you could do the second answer button right above negative. You could go ln of second answer, and that puts the last answer that's in your calculator back into your calculator.
Where is it?
Right above negative. It says A and S.
Oh,
So it just takes that last number, puts it in there for you. Does everybody know where that's at? But you want to put, did you put ln in before it? ln of that number. And then divide by 15. Okay, and our k value here is negative 0.0, let's go to the nearest thousandth again, so 0.84. And like we talked about at the beginning, because this is a decay problem, then my k value should be negative, okay? And that's what it is. It is negative, and that means our value is going down as we go over time. Right, if I write out the equation then, the equation is going to look like this. D of t, this number doesn't change. Like that. Excuse me. So that's our equation, okay? Part B at the top of the next column says estimate the sugar density 5 days and 18 days later. Okay, so I'm going to show you a really quick and easy way you could do this problem. I want to solve or find out how much, what's the value 5 days later or 18 days later. So we're going to put this into our calculator, into our y equals, okay? I mean, you could put each one of those in individually, okay? But if I have to evaluate multiple things, I think it's easier just to put this equation in and then just go to my table and get the answers right off my table, okay? So I'm going to put this in to my So 5 days later, it's 0.174, and 18 days later, it's 0.058. So that would kind of be a kind of a shortcut, maybe. Or you could just plug in if you wanted to. That wouldn't be that big a deal either. Okay. If I had to do the doubling time here, I know it doesn't ask me that, but if I had to do, how long does it take to double here? I would do the ln of 2 divided by that. And that would be how long it takes to double. And you wouldn't necessarily have to put the negative in here. The negative is going to give me a negative answer, obviously. But so that's why we wouldn't necessarily put the negative in this case. But I could do the ln of 2 divided by 0.084. And that would be about 8.3 days. All right, so that's kind of what we're doing here. Just using that formula over and over again, okay? Doing lots of different things with it, finding different values. I'm not going to give you a ton of problems today. Because these have multiple parts, kind of like the examples that we did. 7, 13, 15, 16.